No.
There we go.
That
Yeah.
should be good. Thank you. So yes, I would like to talk to you today about what we're doing at ESO these days, and a little bit what we did in the past, and also what we're going to do in the future. And I would like to maybe also emphasize a little bit opportunities in research and development that we generate, which is something that normally it generates interest, scientists, engineers, companies, and so on. So here's a little collage of science breakthroughs that have been achieved by ESO during its 61 plus years of history. Those are breakthroughs achieved by the community using ESO data taken from ESO telescopes. And on this page, which is only a very quick snapshot, you can see various discoveries and scientific results that actually led to Nobel Prize winning science. There's a lot of course, on exoplanets in the last 25 to 30 years. The very first image of an exoplanet was obtained in 2004 by ESO telescopes. Proxima Centauri has been found by our telescopes to host no less than 2 possibly habitable planets orbiting around it. We've learned a lot about planet formation. First images of a black hole obtained by this network around the world called the Event Horizon Telescope, of which ALMA was one of the main components. Also lots of science around the galactic center, including general relativity tests. And back in the 1990s, also critical observations to demonstrate that the universe is accelerating. It's expanding in an accelerated way. You can hear all these results having had a lot of impact in the past, but of course there's a lot more. Here's the number of refereed publications that ESO enables every year. It's more than 1,000 refereed papers per year now, since 2017. An important point that I would like to make here is that about 45% of these papers use the ESO Science Archive. And I'm going to talk about this a bit later. And actually, between 15 and 25% of these papers only use archival data, which is open to everyone. So anyone around the world can use the ESO archive, and that actually functions very, very well. There's lots of science coming out of archival data. Okay, we're also looking, of course, at the future. There's lots of things that we would like to discover and to study in the future, and here's only a very quick snapshot about it. But of course, visitors to the solar system coming from the outside, the ultimate goal, this holy grail about discovering other Earths, or maybe signs of life elsewhere in other exoplanets, black hole science, but also the formation of stars in the early universe and the gas that it's available to form those stars, down to even doing fundamental physics in terms of measuring the acceleration of the universe in real time. All those are things that are within reach of the facilities that we're building right now. And we have to expect the unexpected. This has been demonstrated every time there's been a new facility in science, in astronomy, in whatever. You always discover something that you did never expect, and that takes probably a lot of driving force in pushing our efforts ahead. So as I said, we were created 61, actually back in 1962, with a mission, which is to design, build, and operate advanced ground-based observatories and to foster international collaboration for astronomy. That's what we have been doing for these 62 years. Our vision, this is the direction that our strategy is taking, is to keep advancing on the understanding of the universe by serving the community, by serving the astronomical community, but also working together with them in ways that you will see a little bit illustrated in some of my slides. We're focusing on world-leading facilities. We're focusing on what our member states individually cannot do alone, that they need to get together to make these things happen. So that's important as well. We don't actually design and develop every single telescope in Europe or anywhere else. It is not part of our vision. We're only concentrating on world-leading facilities. A couple of years ago, our council approved our values. You can see lots of familiar things here, but we take them very seriously. So we try to strive for excellence through innovation, provide outstanding services to our communities. Diversity and inclusion is a key strategy for us, a key value, and sustainability. This will become more and more important, and we're taking this very, very seriously. So that will essentially be a boundary condition for the evolution of our organization and the work that we do. So a few numbers, maybe a few facts and figures. I said it several times. We were founded in 1962, initially by 5 countries. Let's not forget that ESO was cooked in the 50s, in the 1950s, on the ashes of the Second World War. And you recognize that among the founding countries, there's France, there's Germany, which were fierce enemies during a very bad war that happened in the middle of last century. So science, before this funny word of scientific diplomacy that's so popular today, science actually was a handle to start uniting Europe around astronomy. Today we have 16 member states. Since 1963, in addition, we have a very strong partnership with Chile, which hosts all of our telescopes today. And in 2017, we started the 10-year partnership with Australia on part of our program. That partnership is expected to potentially give rise to Australian membership of ESO towards the end of that period. We're starting to talk about this. To give you a flavor of the size, there's about 750 people working at ESO of 30 nationalities. There's a number of Brazilians, by the way. 450 of those people work in our headquarters in Germany, the rest in Chile. We get an income of about 228 million euros every year. The contribution to this funding is in proportion to the gross domestic product of all the member states. That's important. It means that we don't discuss this. We fix the budget that everyone knows how much they have to pay. The expenditure, the amount of money that we're spending now is a lot more, in part because of delays in the ELT construction costs, but also because we have tools to move money forward if need be. We have an agreement with the European Investment Bank that we can borrow essentially money from the future to within some conditions. Important point today, we're spending about 60% in development of new telescopes, facilities, and in new technologies. The remaining 40% is for operating the organization and for operating the existing observatories. We play quite a critical role in international policy, in international science policy in many environments in Europe, but also in the United Nations, in particular in trying to protect the sky from mega constellations and other disturbances that put at risk the future of astronomy. And we have really very close relationships with the European Space Agency, with the Square Kilometre Array and CERN as well, and many other organizations. So this is a photo of our headquarters in Garching. This is near Munich. I'm actually in Munich now. This is half an hour with the metro, very close. And what this is actually, it's a development center. I mean, more than half of the people working in those premises are engineers. We also have a fraction of scientists. We have administration. Our scientists and our engineers, besides developing new telescopes, instruments, and technologies, here in Garching, they also operate the back end of our observatory. So they are the ones who manage the data that we get. They produce the archive, they curate it, they produce the pipelines, and that's what makes our observatory so powerful. And also, all of our scientists can devote, or they are expected to devote a fraction of, sorry, I think I have moved from full screen presentation for some reason. Let me go back. So a fraction of their time they're expected to do research in astronomy, which is very important to keep engagement with the scientific community. But as I said, what we have here in Garching is mostly technology development of telescopes, of instruments, two integration calls, lots of laboratories, and so on. In Santiago, in the capital of Chile, we have a little compound there with the administration, also research, and in the future we'll be moving lots of operational activities to that campus, which is inside the city, because we're moving towards a new operational model for the observatories, where we will need to send less people to the observatory sites. That, as you will see in a moment, they are very remote, and we believe that we can do a lot more from a centralized place on these operations. So this is our observatory portfolio. We have telescopes in 4 places, in La Silla, in Paranal, in Armazones, and in Chajnantor. All of these places are in the Atacama Desert, in the northern part of Chile, and I'm going to go through what we have in there and what we're planning to do in those places. So La Silla, that was the very first observatory that ESO established 55 years ago already. That we passed that milestone a couple of weeks ago. As you can guess from the pictures, there's many telescopes there. They are typically small telescopes. Not all of them are operational. Those are telescopes mostly from the past, but a few of them we still keep operating and delivering data. And in particular, those two that you can see here, the 3.6 meter telescope, which is mostly dedicated to measuring radial velocities using very high precision and very stable spectrographs, both in the optical and in the infrared. And also the new technology telescope, a 3.5 meter telescope, that was the first one in the world to use active optics. This means the correction of the shape of the mirror when we point, when we move the mirror to point not exactly to the zenith, but somewhere else in the sky. The gravity, the force of gravity, distorts the shape of the mirror. And this was the first telescope in the world to correct for this actively. That's why it's called active optics. Of course, all the telescopes in the world now use this technology. We have a lot of what we call hosted telescope projects in that mountaintop as well. Those are small telescopes established, operated by universities and by R&D institutes in our member states. And what we're providing to them, it's the services and the basic infrastructure services and the technical support when it is needed. But altogether, they constitute quite a powerful set of telescopes, of which ESO doesn't have any observing time. But that's what La Silla is today. It's a platform for these hosted telescopes, dedicated each one of them to very specific science cases. So Paranal, this is the most powerful optical observatory in the world at the moment, the very large telescope. You can see another picture here from above. This is not actually one telescope, it's a number of them. You have these 4 bigger telescopes there. Each one has a primary mirror of 8.2 meters in diameter. On top of this, there's these smaller telescopes that we call auxiliary telescopes. They are much smaller, but what they can do is to move. They can be placed in different configurations there. So under this mountaintop, under this platform, we have a big infrastructure called the interferometer, the VLT interferometer, which can deliver interferometric observations of 4 of these telescopes, either the 4 big ones or the 4 smaller ones, in infrared wavelengths. This is not like radio interferometry, which is, I would say, a bit easier, because in radio interferometer, what you do is you digitize what you observe in the sky locally in every antenna or in every telescope, and then you correlate these digitized signals. Here we cannot do this. We actually make active interferometry between the light that comes through these telescopes, and that is incredibly powerful. That delivers the resolution of a telescope that would be as big as this entire platform. So something like 130 meters in diameter. Of course, not the collecting power, not the collecting power for the light, but certainly the resolution. And this is an amazing resolution, and there's big discoveries using this. So very powerful compound. On top of this, we also equipped one of the telescopes with another technique, which cannot be confused with the previous one, which was active optics. The active optics, what it does, it's to keep the primary mirror in shape. Here, what we do is something different. We actually try to counterbalance the turbulence in the atmosphere, because that turbulence generates lots of fluctuations that change very, very rapidly, down to very short time scales, like 10 milliseconds. So this is why we actually at ESO have developed these lasers, that these high power lasers, sodium lasers, that are now used by many telescopes around the world. What we do with them is that we create 4 artificial stars in the direction where we are observing, because those sodium lasers, they get reflected in the higher levels of the atmosphere where there is a lot of sodium. So we collect the reflected light of these 4 artificial stars in a device called wavefront sensing camera. And by following their movements due to the changes in the turbulence of the atmosphere, we're telling the telescope, we're telling the secondary mirror of the telescope that it has to change its shape. So we keep the image of those 4 lasers always in the same place. And with that, we achieve an amazing spatial resolution, actually better than when you go to space. So this is really a very powerful tool, adaptive optics, which is, by the way, not only used in astronomy, it's also used in ophthalmology and also in imaging of live tissues, trying to get the 3D, the tomography of live tissue. So very powerful technique that took a lot of effort to develop. And this I have already mentioned, the VLTI, the interferometer, acts as a 130-meter telescope. And this is part of the infrastructure that we have below this platform. This has to combine the light of these 4 telescopes to a fraction of a wavelength and in phase. So this is very tough, but it works. So we have achieved those 2 techniques to have very high resolution images during years of development. Now, part of the trick of Paranal is that we at ESO don't develop the instruments. We only partially contribute to them, to the cameras and spectrographs, and we do it in partnership with consortia of universities and institutes in the member states and beyond. And the advantage of this is that this is all science-driven. So we have this many institutes that really what they want to do is science. They want to build instruments that deliver unique science that it's not achievable otherwise. Then we normally make calls, and then the institutes engage. They lead the development. We participate. We provide them funding, and we do all the reviews because we're also the final customers. But at the end of the day, most of the contribution, or a big part of the contribution, comes from these institutes in the member states. And this investment we reward by giving this consortia guaranteed observing time in our telescope. So in that way, they can execute very challenging, very big observation programs that they wouldn't be able to do in a different way. So at the end, these instruments come to our observatories. They are commissioned. We receive them, we accept them, and we operate it for 10, 15, 20, or even 30 years. And then the entire community benefits from that. So it's a sort of virtuous circle here that we're establishing with the R&D institutes in our member states. They benefit because they can achieve very challenging science goals, and we offer it to the entire community, which also makes very good use of them. We have a variety of instruments in Paranal, something like 15 at the moment. Each one of the 3 telescopes can operate independently. They can also use the interferometer. And there's even one instrument that simply what does is to collect all the light that comes through the 4 big through the 4 big telescopes and put it into a single spectrograph. This is more or less equal to the power of a 16-meter in diameter single telescope. We're continuously updating this. We're developing new instruments, not maybe as fast as the community would want, but be aware that there is a lot of effort, and every one of these ventures, every one of these instruments takes 10, 12 years to develop, and that's a lot of time and a lot of effort for everyone, for ESO and also for the community. Okay, so our other big observatory in operation is ALMA. This is actually not an ESO observatory only. We share it with Japan and with the United States. We have built it together. We're operating it together. And this is a radio telescope operating at millimeter and submillimeter wavelengths. It is at 5,050 meters of altitude. That's what you need if you want to observe at high radio frequencies, at sub-millimeter wavelengths. So we have very little atmosphere, only half of it above you, and it is in a very dry place. So there's very little water vapor above you. So that means that there's windows of observation in the electromagnetic spectrum that are only accessible from a site like this one. It is a very big thing. It has 66 antennas. They can be positioned in a number of places along this big plateau. Maximum distance between antennas 16 kilometers. On top of on this place, we also have this building that you can see. It's a technical building. That's where we have the correlator. Here it's a classical radio observatory. Every antenna takes the signal from the sky. It mixes it, it digitizes it using the clock that we maintain inside. And then the digitized signal goes back to this house here, and it's correlated in a big supercomputer that was developed for that purpose. And you can see that yellow thing there. This is a transporter. We can move these antennas and make different configurations. The more separated you put the antennas, the higher the resolution that you will achieve. The closer that you put them, the lower resolution, but the bigger field of view that you will be able to observe. So there's this compromise, and we're changing the configuration of the array, of the antenna array, every year, essentially, or every other year. So here's some of the technology that I explained, the antennas, the correlator, one antenna being moved. And also this is a front end, what you have at the bottom right there. So this is what's on every antenna to digitize, to receive and digitize the signal. And you can see that there's a number of receivers there operating in different bands. And I'm very happy that finally we are now equipping the last empty slot in that front end. So all the receivers are now in place. They are all developed, and actually we have started to develop new ones to use newer technology. 11 years since ALMA was inaugurated. That's a lot of time, many science breakthroughs. We're now in cycle 10 of the observations. One interesting thing is that we now offer observing time together with the James Webb Space Telescope, also together with the VLT and together with the VLA, which is a centimeter, very powerful radio observatory in the United States. Bad news is that there's a huge oversubscription factor. Probability of obtaining time, it's 1/8, which is very little. By the way, I need to clarify this. The observing time of ALMA has a reserve of time for anyone outside the partner regions that wants to apply for observing time. So it is possible to obtain ALMA observing time from outside of the ESO region, outside from the United States, and outside of Japan. And of course, the ALMA archive is also open to everyone. We're now engaging on a big development project of ALMA, so taking a step to make it more sensitive. We call this the wideband sensitivity upgrade. This is the highest priority. We need to replace the correlator that I showed to you, but also to develop a few more things in there. And we're starting to work on this. It's really a heavy commitment for the next decade with lots of investments from the three parties. Yeah, and so this is the ELT, the Extremely Large Telescope. This is what keeps us busier at the moment. The ELT will be the largest optical infrared telescope ever built or planned. The primary mirror will have almost 40 meters in diameter. This is huge. The biggest, the optical telescope, which has the biggest primary mirror today, has something like 10.4 meters. This will be almost 40. So this is really a gigantic step forward, very challenging. It's, of course, not a monolithic mirror. It's made of tiles, of hexagonal segments, each one about 1.5 meters in diameter. And it has 798 of them. And we'll, of course, use adaptive optics in the way we have learned from the VLT. Construction started in 2015. We hope to have first scientific observations towards the end of 2028. Of course, this is under threat, as you can imagine. The cost is large. It's 1.5 billion euros, plus support that the organization provides, plus also the contributions to the instruments that the consortia of institutes from our member states and beyond are investing in delivering this first class of instruments. It is at the moment being erected in Cerro Armazones. This is only 24 kilometers away from Paranal, at 3,049 meters of altitude. This will not be a separate observatory. It will be operated together with the VLT in Paranal by the same people and the same infrastructure. What you can see in there, it's a photo which is probably 2 months old, so there's been lots of progress in between, but you can see essentially the structure of the dome already placed, some of the cladding, some of the covering of the dome also in place. This thing on the base is the auxiliary building, and this is really moving now very, very fast. As you probably know, there's another 2 ELT projects led by the United States. One is called the Giant Magellan Telescope, which has participation from the University of Sao Paulo, I believe, or from the state of Sao Paulo. The other one is the TMT, the 30-meter telescope, which is also led by the United States. Our BLT is a lot more powerful. It's a lot more advanced than any of the other projects. Some people tell me that it's 10 years that we're ahead of them. And it's the only one that it's fully funded. So we have all the money to finish the telescope and put it into operation. And we also have the budget for operation in our budget. So here's a few numbers. So you get a flavor of what it is. It's like a football stadium, right? It's I should be careful not to mention Maracanã here. I'm in the wrong place for that. Maybe the Camp Nou of Barcelona. That's a lot better. The auxiliary building has 110 meters in diameter. The dome itself, it has 77 meters in diameter. The telescope structure has 55 meters in diameter. So this is all huge. The dome will have 85 meters of altitude when it has these doors. So it's a gigantic construction, and the difference with the Camp Nou in Barcelona, this one, the dome, for example, needs to be precise to a millimeter scale. So it's 2 millimeters of tolerance that the dome has, because otherwise it would not rotate. And companies that build stadiums and things like that, they're happy if they have a couple of centimeters of tolerance. And we're doing it much harder, but this is necessary. So I think I have a quick 20-second time lapse here with what happened last year. That was at the beginning of 23. And you can see what happened during the year. The dome was being erected, and yeah. So that's getting to the end now. So that's how it was in December. There's been much more progress since. And you can see below bits and pieces of not only of the dome, but also the telescope. I think I have another picture. Actually, we have passed 50% completion in the construction of the ELT, with the mirrors, with the control systems, with the mechanical structures. We're really very, very well advanced. Actually, the first segments, polished segments of the primary mirror, arrived already at the observatory in January this year. And this morning I was told that we have already coated 15 of them. So we have already 15 of those 798 segments which are polished and recovered with this reflecting material, ready to go to the telescope when it's there. This is the first generation of instruments. There's 4 of them. There's spectrographs, there's an IFU, there's a camera in the mid-infrared, and there's also an adaptive optics fit. Those instruments are in various stages of final design review. Actually, METIS, which is the mid-infrared instrument, it's actually about to close final design review. They have ordered most of the pieces now to industry, so this is really moving very quickly. Of course, full of challenges. These instruments are extremely complex, extremely big. There's large consortia behind them, very risky. The cost of any one of them, it's probably about 100 million in total, and they would require of the order of, we believe, 1,000, almost 1,000 FTEs, 1,000 years of work. So there's 1,000 person work years in each one of them. So it's a huge effort involving many, many partners also outside of the ESO member states. Okay, and last but not least of our infrastructures in the planning, this is the Cherenkov telescope array. This will be the very first observatory of very high energy gamma rays from the ground. We're talking about from a fraction of a tera-electron volt to tens of tera-electron volts. There will be 2 arrays, one in the north in the island of La Palma, the other one in the south in our territory at ESO, between Paranal and Armazones. We hope that the construction can start shortly. Actually, we have already started a little bit the infrastructure there, the road, the access road to this place, it's already built. Now we're moving on with the foundations where the telescopes will be sitting with the connection to the power grid and a few other infrastructure contracts that we expect to play very soon. So this is what actually we have in Chile. Not bad. This is, you can see this Google map. No, it's not a Google map. That's an actual photo now that I remember, taken from a drone, I think. So this is the place where we're going to build the ELT, where we have Paranal, and the circle on the right is where we're going to place the southern part of the Cherenkov telescope array. This is all a triangle, 25 kilometers at the site. So very powerful place, actually, probably the biggest hub in astronomy around the world. On top of this, we still have ALMA, of course, which is further away, in La Silla, which is, as I said, this platform for relatively small projects. Very, very powerful, actually. We attach a lot of importance to data management at this. So I explained at the beginning that we make extensive use of data archives, but there's a lot more about this. I mean, we're now closing a project, not closing, we're halfway through it, which we call the data flow system, which is an end-to-end flow system where from the time that an astronomer submits an observing proposal to the day that the data had been taken and had been put in the archive, there's a single link between those 2 points, going through the circle, which includes the data acquisition, the planning for the observations, the archival, the quality control, etc., etc. So that's what makes our observatory so powerful, because of the effort and actually the cost that we invest in data management. And our archives are fair, they're findable, accessible, interoperable, and reusable to the highest standards. And whenever we can, we also provide advanced science products like extracted spectra, fully calibrated spectra, and even, occasionally stellar classifications, redshifts, whatever. I mean, we rely very much on the effort of the community, and this is almost uniquely related to large programs. But those advanced data products are of very, very high value, and the community makes very good use of them. Okay, so let me talk a little bit about a different angle to all of this, which is sustainability. I have spoken about sustainability at the beginning and service to society. I have also told you that our member states invest 228 million euros in our business every year. If you divide this by the number of inhabitants of our member states, I think this comes down to about a cup of coffee per person per year. But that's, I mean, it's not every person who pays that, it's the governments. And they need to make sure that their investments are actually impactful in society and not just for the scientists, which of course are the most important beneficiaries of all of these activities. So 2 or 3 years ago, we did a study of this about the impact areas of ESO generally. And we found together with a consultant that we're actually impacting on 5 different areas. One is science and engineering. This is very obvious, but still worth remarking. Second, in economy and innovation, although we're relatively small. I mean, we don't generate economy of scale, but we generate a lot of know-how. Talent development, we put also effort into this education and outreach, and also our investments in international collaboration and policy. And I want to make a couple of remarks about this because that is quite important what we're trying to achieve here, in particular in terms of sustainability also, which I would like to make it clear that for us sustainability, it means 3 things. It's not only environmental sustainability, it's also societal sustainability and financial sustainability. It doesn't help if we save the planet at the expense of killing the people. So those 3 things need to go together, and this is our very clear understanding. We're very strongly subscribing to the ESGs, to the United Nations Sustainable Development Goals, and this is the way we understand this. But speaking about environmental sustainability, there's lots of things in here. And back in 2019, we did an audit of our carbon footprint, which is, of course, an indicator of all of this. And it surprised us, it doesn't surprise us anymore, that the main generation of carbon footprint from ESO, it's energy. It's the energy that we need to be provided with. And this, in 2018 was still news. It was not so clear. Now it's super clear everywhere. I mean, this is what is driving development, and of course, it's what is driving carbon footprint, energy. Having access to energy is critical. So we've taken some actions here. In particular, we have developed a photovoltaic power plant in this big hub in Paranal, Amazonas, which is able to support everything. More than 50% of our power now comes from this photovoltaic plant. Of course, that during the night doesn't work, but you may be surprised that we spend most of our power during the day in the observatories, because that's where we have to cool the air inside the domes to make sure that we don't have turbulences at the beginning of the night. So that's really working. It's taking away quite a lot of CO2, of carbon footprint. Our observatories are in a very remote place, all of them. We need to track the water there, electricity, other than from the photovoltaic plant that we also secured. And there's a lot more aspects here. And this is our carbon footprint evolution during the years. Of course, you can see the pandemic here very clearly, but the measures that we're taking, they, despite the fact that we're doing a lot more things that in 2018, means that we have at least managed to contain the carbon footprint. And I'm sure that we're going to reduce it in the future through a number of measures that we're implementing. So this is the photovoltaic plant in Paranal and Amazonas, 9 megawatts. This is a lot, and we're very proud and happy to have done this. Okay, so let me talk a little bit about opportunities now. We're walking towards the end, so we have ample time for questions and answers. Data access. This is one very important point here that I want to raise and raise in all my presentations. It's again about the Science Archive facility that you can access just clicking into this website, archive.eso.org. You have to, I think in the most recent version, you don't even have to register unless you want to access proprietary data. So this archive facility contains all the data obtained by all ESO's observatories ever. since 1996. We normally grant a 1-year proprietary period to the team, to the astronomers who propose the observations, so they can take their time in exploiting the data, in introducing, in analyzing, in writing their papers. Except for public surveys. We occasionally do public surveys where we launch calls for ideas to the community, what type of public surveys they would like to do, big imaging or spectroscopic surveys, and then there's no proprietary period. Public surveys go immediately into the archive. Anyone can use them. But those who are not public surveys, they are also public 1 year after the data were taken. We make available both the raw and the advanced data products. We have now a single guest user interface for La Silla, Paraná, for our optical observatories, and also for ALMA. You type your coordinates or you click on a place on the sky and you will be led to where you can download all the data existing, both from optical and radio observations that we have. And very importantly, we also have available data reduction tools. Here we rely on the community as well, but it is a requirement that they make this data reduction tools available. And this is a policy point. It's very important. And there is a big trend in Europe these days, driven by the European Union, about this European Open Science Cloud. Of course, we have been doing this for 30 years, but now it is being enforced in all research infrastructures, in synchrotrons, in particle accelerators, in everything. And we're very big supporters of this as well. Observing time. This is another interesting one. Of course, if the data that you want, it's not in the archive, you may want to have access to observing time. I'll tell you one thing which is very clear. In our optical observatories, proposals are evaluated and time is granted and scheduled based only on scientific merit. We have committees. We are now implementing, we have already implemented since about 1.5 years ago, what it's called distributed peer review. But all the proposals are anonymous. When evaluators see these observing proposals asking for observing time, they don't know where they come from. They have to assess them only based on the scientific value. This is how it works. So every year we grant observing time to scientists from non-member states and neither from Chile to a significant amount. And this is something that our council is comfortable with, and this actually enhances the value of the observatory. In ALMA, it works a little bit different. We split the time between the 3 parties, between North America, Japan, and us. But as I mentioned before, we reserved typically 5% of the observing time to be allocated to scientists from outside the 3 regions. The reality is that there's not so much time allocated outside because there's a lot of people proposing from the inside, but still 1 or 2% of ALMA observing time goes to outside the partnership. For the optical telescopes, we issue a call every 6 months, although starting sometime in 2025, this is going to be only yearly, only once per year, but we will add a fast track channel, probably every 6 weeks or something like this. We will open for proposals that could not be submitted on the yearly call. And for ALMA, it has more or less always been on a yearly basis. So this is very much like all the space observatories do as well. I said it before, but I want to emphasize this. The time allocation has 2 important policies implemented. One is the double anonymous reviews. The evaluators do not know who is submitting. And now also the distributed peer review, which for small proposals, instead of being discussed in a panel, we distributed to 6, 7, 8 members that have submitted other proposals to evaluate those smaller proposals. And that seems to start to be accepted by the community. In our view, it works well. And this is how it's it's working now. We're continuously scrutinizing potential biases, in particular gender, language biases, and so on. Even if proposals are double anonymous, the way different genders write proposals, it's different, and that still causes a little bit of a bias that we really are trying hard to avoid now. But this is only to say that scientific merit, it's what counts here. Another one about opportunities, it's about jobs. I said it before, we have a number of Brazilian employees at ESO. And also, in our vacancy notices, it says that any nationality is welcome to apply, and we don't look at it unless there is, let's say, a very equal merit in a particular position. Then we would actually appoint the person from a member state or from Chile. But I mean, that happens very rarely. So job opportunities, you can find them in this web portal, jobs.eso.org. We have a number of them all the time. This is for international staff members. For local staff members, you have to be resident in Chile. We also have fellowships for science and for engineering. This is for postdocs. Those are for 3 years in Germany, in Garching, and you have 50% of your time to do science. Sorry, 75% of your time to do research, 25% to do some functional duties. In Chile, it's different. You have something like 60% for research and 40% for functional duties. Essentially, people go to the observatories to do service work, to do observations. But then this is 4 years. And the 4th year, you don't do any functional duties. You just can go to a place of your choice. ESO will still pay you, and you just do research in there. Again, nationality doesn't play a role in case of only in case of equal merit. And since 2022, we have released diversity, equity, and inclusion, which we're taking very seriously. And this is now folded in our recruitment processes to make sure that we have equitable policies in place for our recruitments. So that's my last slide now. I want to make an important comment at the end. I believe that after 60 years, we can sort of be happy what has happened so far. Our telescopes have been data drivers for many scientific breakthroughs. Support from the member states remains critical. This is very, very important. We don't rely on private investments. We learn the tough way from other initiatives that this doesn't work at the end of the day. Our partnership with the community is super important in this instrument development business, but also in prioritizing what we want to do. The engagement with the institutes on instrument development is critical, and you can imagine that building a big telescope requires a lot of partnership with industry as well. It needs to be there and needs to be ready to take very challenging contracts with us. On the ELT side, we're doing, of course, we have lots of challenges still ahead of us, but we're doing very well, I would say. We will deliver to our member states the most powerful of the extremely large telescope, probably a decade before anyone else. That will mean that Europe, which actually started ESO in 1962 for the reason that the United States was way above and were way more advanced than Europe in terms of telescopes. That's why ESO was created 61 years ago, to try to not lose too much against the United States. And now, after 62 years, I'm very proud to say, because I have very little to do with it, so I can say it with pride, that we're ahead of the United States in ground-based facilities. So this is really a very important achievement. The last point I want to make is that now we're heading towards assembly, integration, and verification of the ELT, of the extremely large telescope. That will mean a lot of work. Lots of people will have to go to Chile to install the optics. electronics and make it work of the telescope, of course. But we are starting together with our council to look at what we're going to do after. Because in our vision, we say that we will keep working together with the community in developing the most powerful world-leading telescopes and instruments in the world. So we're starting to discuss with our council how we're going to do this, which process are we going to follow to understand what we may be doing after the ELT. That probably will not, that new project, that new program will probably not start before 10 years from now. I don't know. It depends on how things go. But we need to start planning for it because, you know, it takes a lot of time to plan. It takes a lot of plan to make sure that the community is behind the decisions that our council will ultimately make. And it will take also a lot of time for the organization, for ESO, to take ownership of a new program. So it's time to start thinking about this, and we're going to be talking and listening to the community in the next 3 to 4 years about this until our council makes a decision. And with this, I think I'm going to stop. Thank you very much.
Javier, questions? Seminário. All right, go ahead.
Can you hear me, Xavier?
A little bit, yeah.
You better come over here.
Yeah.
You guys want to raise a question, please come over here.
Hi, Xavier. Oh, it's frozen.
Sorry.
I think you're frozen for me.
Can you hear us?
Sorry, we've lost the. I don't see you moving, and okay. Now
you're
I
back.
see.
Now you're
Now
back.
it's
Yes. Yeah.
Hi, Lucimara
Oh.
Martins here. I have a question about the adaptive optics. ELT, if I'm not mistaken, originally was thought to be mostly a near-infrared telescope, and most of the instruments are actually in this area, but now people are pushing instruments for the blue. And we know the adaptive optics are mostly working in the infrared. Is there any research for adaptive optics in the blue? And do you think of anything of the sort for ELT?
Not specifically for the ELT, but we are developing for the VLT a multi-conjugate adaptive optics instrument that will work not in the blue, but you know, in the optical band. So we will see how it works. Yeah. For as you said very well, we have one of the first line instruments, which is called Harmony, which has a visible channel, visible reaching down to maybe 500 nanometers.
Yeah.
And will in principle it should work. We will see to what performance. But yeah, I mean it is tough. I mean adaptive optics in the blue is very tough. And yeah, one of the second generation instruments for the ELT, it's called Andes. It's a high resolution ultra stable spectrograph which has a visible and an infrared channel, but that does not actually use adaptive optics. So yeah, that's where we are at the moment.
Okay, thank you.
Welcome.
Hello, I'm Jennifer. Can you hear me?
Yes, I can hear you very well.
Okay. First, thank you for your presentation. I'm an engineer, so my question is about the place that will receive the telescope. Is the time and the cost of the place construction included on the time and the cost of construction telescope?
Sorry, I hear you coming and going. Could you repeat? I mean, I see you sorry, I see you well, but the sound, it's broken from time to time. Could you repeat a little bit the question,
Yes,
please?
yes. My question is about the place that will receive the telescope. So is the time and the cost of place construction included in the time and cost of telescope construction?
Yeah, the cost to complete that I showed is everything. It's absolutely everything. It is not only the fancy stuff. It includes the road that we had to build.
Yes.
To the preparation of the mountaintop, all the civil construction work, the salaries of the people that have to do this, what we have to buy, what we have to pay to the to everyone. So everything is part of this 1.5 billion euros.
Yeah.
What we don't include in there is, for example, the time that I'm spending on the ELT, or the time that our administration is spending on managing contracts, on recruiting the people. So those are services of the organization that we provide to all of our programs. So that we don't charge. It's not included in this 1.5 billion. If I were to put everything together, the direct cost to complete, plus all this organizational support, plus also the contributions from the instruments that we don't pay directly, we're probably talking about a lot more than 2 billion euros. Yeah.
Okay, thank you.
Welcome.
Questions? Okay, I have one question for you. But when you talk about the archive data, I imagine that probably for most telescopes, especially in the optical, this must be fully reduced data, right?
This is what we call the advanced data products. Yes,
Right.
You can both download raw and reduced data. Yes.
Right. So the same rule applies for ALMA data. So can we
Yes.
get the fully processed ALMA data?
Yes, that's what you get by default. If you are a black belt in radio interferometry, you can redo the whole process if you want by changing parameters. But you need to be a black belt to do this. No, for ALMA, you get actually the scientific data.
Right. I'm asking this question because the JWCT, they say it's available, the whole data, but what's available actually is the raw data. If you want to take their images, for instance, and use it for scientific purpose, you have to do it yourself, which is not always a simple thing to do, unless you have a pipeline in advance to do it. So I imagine that it's a policy from ESO that you provide fully reduced data. Is that correct?
I think it is. I think this is correct. Even so, we have 3 levels, right? 1 is raw, 2nd is reduced, 3 is more advanced data products. And yes, our compromise for all the data, it's level 2. Level 3 will reach in some cases.
All right, I see. Okay.
Yeah.
Questions about that?
Good afternoon. My question goes more to the geopolitical side, actually. In a context of war in Europe, are you hearing me?
Not well. I have cuts now. Try it again.
Okay. In a context of war in Europe and increased investments in the military area, especially in Germany, for example, do you believe that it can affect the investments, for example, in ESO or big projects, or any indication that it can happen in a near future or midterm, maybe?
Thank you. Yeah, that's a highly political question. I don't know. I mean, this is, of course, a challenge. We have been relatively lucky with the ELT that when the invasion of Ukraine started, essentially we had bought everything. So we didn't have a huge impact in the price of the pieces of the steel in particular, which was one of the big things. So of course, due to the post-pandemic and the wars and so on, prices got up, and we had to deal with this. That was tricky. Whether our member states will be happy to invest into a new project in a context where they are increasing all the defense budgets, that is something that we don't know today. But we hope that it's two different time scales. I mean, we're talking here, our big projects take 20 years to develop. And I would hope that in 20 years from now, the geopolitical context has changed a lot. So I hope that this long-term vision will dominate this discussion and not the short-term episodes that we're experiencing now. But this will have to be seen. Our first discussion with our member states has shown no issues about this, but of course they always say, yeah, I mean, we don't know what how much the geopolitical situation will drive the economy in the member states. So we will see. So planning for success is a must. That's our strategy.
Hello? Can you hear me?
I can
Yes.
hear you, yes.
Thank you. Some time ago, I had heard about a possible future instrument that would extend the musical abilities to the blue wavelength range, the blue muse. Do you have any updates about the instrument?
Yes, yeah, precisely. So Blue Muse, we're going to start the phase A now. We actually started it last week. So I made it a requirement that we would have our previous instrument for the ELT finalized. That instrument is called ERIS, and thankfully we fixed the last technical issues in January. So we're now ready to start the phase A of Blue Muse. Yes, yeah, and I actually reporting tomorrow to our scientific and technical committee that we're starting Blue Muse now. Yeah, that was the second priority. That's our plan for instrumentation in the VLT dictated, and it's been delayed, but we're starting it now. Yeah.
Great, thank you.
Any other question? Actually, I have another question, which is,
yes,
I remember seeing a picture of the headquarters, the ESO headquarters, surrounded by technology companies. Could you tell us exactly what is the relation between ESO and those companies, and how they come on board with investment, specifically on instruments for telescopes?
So physically speaking, there's no link there. I mean, we're sitting in a campus which is owned by the Technical University of Munich, and they have expanded, and now they have quite a few high-tech companies in the campus. But to the best of my understanding, we have no relationship with any of them. So there's really, for us, there's no synergy with these companies. But it would actually be tricky to establish any specific relationship with them, because our procurement rules are very clear on this. We need to all of our call for tenders and so on. We need to open to all of our member states. But in practice, there's no. I mean, most of our providers in the campus are service providers. They are not, high-tech enterprises at all. What it's a lot more beneficial is other research institutions in the same campus. Then yes, then we have lots of synergies. In particular, there's an institute next to ours, which is the Max Planck Institute for Extraterrestrial Physics, which spend lots of effort in developing new instruments. And some of the most celebrated instruments that we have in Paranal. They were developed by consortia led by these people. So there is a lot of synergy, but not with companies.
I see. Terrific. Question? Go ahead.
Hi, Xavier, me again. Just a curiosity question, actually. You were talking about, the last slide was talking about the post-ELT planning. How does it work? Do you get a commission to think about this? Do you open calls for people who have ideas for instruments? Only ESO members participate in this? How does it work?
So we're talking two different things here. One is the development of the existing observatories. So for the VLT and the VLTI, we have a budget line for new instrumentation coming in. And this we plan more or less on a decade-long time scale. And last time it was in 2019, where we had a workshop that is so-called VLT 2030. And out of that workshop, we are now doing Gravity Plus, which is an upgrade, a serious upgrade of the gravity instrument for the VLTI, and we're now starting Blue Muse. But this has its own life. And for ALMA, we also have a roadmap for developing ALMA, but with a fixed budget line, which is this wideband sensitivity upgrade project. But what I'm talking here is about a new telescope, let's put it like this, or a new adventure of that size. It doesn't need, so we're still, as I said, I still need approval from the council on the process and how we're going to approach this. But my proposal is that essentially we will be talking to the community for about 1 year, explaining what this process is about. Then we will issue a call for ideas only. They will be assessed scientifically, and they will be assessed also by us about whether we can take ownership of this project, about estimates of costs and things like that. And there will be a process for council to say, yes, this will be our next project when we have the money to do it. So that's essentially the process. I envisage that we're going to spend 3 to 4 years on this process, which is, I think, the right time frame, because we want to get the community behind. And but the details that you're asking me, those we still have to develop.
Yeah. Okay. Thank you.
But it's this is more or less the scheme that we intend to follow.
Right. Any other question? All right.
Hello again. I have a curiosity about if there is something that could stop the construction of the telescope. For example, if during the construction they find something very, I don't know, there is something could stop the construction.
Yes, and with yeah, there was a pandemic. you may remember. Yes, there was a pandemic, and that came on a very bad time, especially for the work at the site. I mean, some of the companies in the companies that produce the glass or the electronics, they only had to stop for a couple of months and they kept working, right? But the construction at the site at Amazonas, that stopped for 1.5 years, almost 2 years actually. And it was a combination of the pandemic with other circumstances. In fact, the consortium that it's building the dome and the main structure of the telescope at the site, and be aware that this is a contract that it's 450 million, right? So only this piece of the telescope, the dome, and the main structure is 450 million euros. This is a consortium of 2 companies, of 2 Italian companies. One went bankrupt in 2019. The lead company went bankrupt in 2009. And okay, we managed. The other company took over, and then they also went bankrupt. Well, not exactly bankrupt, but they got into serious financial difficulties in 2022. And in spite of this, we managed, and they managed to survive. We put a contract amendment with them, and they are working like hell. They are working very, very rapidly. So that we have already experienced. What else? We could have a big earthquake. Remember that Chile is a big, it has a lot of seismic activity. So a big earthquake could actually provoke a very serious trouble in there. There's many risks. We have lots of risks in our risk register. And there's many of these things that if they materialize, they could stop work. We also have mitigating actions for most of them, but there are some that it would just be impossible because it's too big. So I hope that none of the most important risks, which have no mitigating actions, do not materialize, but I cannot tell 100% sure.
Okay, thank you.
You're welcome.
If there are no questions, let's thank our speaker again.
Thank you.
Thank you very much. Thank you, Javier.
Thank you.